Okay, so the last thing that I want to look at with exponents and logarithms is kind of some real-life applications of those scenarios. So we're going to look at exponential growth and decay. So we've kind of already talked about this when we started talking about exponential functions, but exponential growth, if you describe something as exponentially growing, it means more than the values are just increasing. It actually means that the growth is getting more and more rapid as time goes on. So growth that increases more and more rapidly over time. So exponential growth sometimes explains things that kind of get out of control. They start off being small quantities and then they just keep increasing forever. So some real life examples of things that can grow exponentially. Bacteria, definitely disease, okay, like viruses, population of humans, of animals, of anything, okay, but also compound interest. We talked about that when we looked at like compounding money a certain time frequency. So money can also grow exponentially. And so there is a general formula for exponential growth. And if you remember when we talked about money, I think this formula won't surprise you as far as what it looks like. And it's actually going to hopefully remind you of one of the two finance formulas we already talked about. So here's the general form for exponential growth. It's A equals A, and you say that as sub-zero. It's a subscript instead of an exponent. It's like little, but it's down below. And then e to the kt power. So just to kind of let you know what each thing is, A is the amount after time t. Okay. In this case, though, with money, we were always talking about years. And just know that, like, here, we may not be talking about years. With bacteria or, like, disease, it can grow by the hour sometimes, okay, or even by the minute if it's super, super aggressive. A sub 0 is going to be the initial or starting amount. But it's sub 0 because it's time 0, so it's like the amount at the beginning. What do you guess T is going to be? No shocker. Time. And then K is going to be the growth constant or the growth rate. Do you notice that this looks awfully close to the PERT formula that we did before when we talked about money, right? It's just that we're using different letters, right? But P was the starting dollar amount, right? R was the interest rate instead of K, and then T was the time. So the biggest thing is you need to kind of pay attention to K, rather. K is, like I said, it's the growth constant. It's often a percentage when you're describing it, but for the formula, change it to a decimal. So we're going to look at some exponential growth problems here in a bit. But before we do, I want to also talk about exponential decay. Now, you probably don't have as much experience just in your everyday life with things that exponentially decay. But it is, instead of a growth, it's a decreasing of values. And they decrease more rapidly as they approach 0. So growth situations mean the values are increasing. Decay situations means the values are decreasing. So let's look at some examples of some things that exponentially decay. Unfortunately, if you don't have a winning investment or an investment that earns you money, you can lose all your money in the stock market, right? So money in a losing investment will continue to decline until you have how much left in your account? Zero, right? That's the gamble with the stock market or with investments or whatever, okay? But something you probably maybe have heard if you watched documentaries or something, but have you ever seen like documentaries where they try to date artifacts? Like they dig up some artifact in Africa or something and they're trying to figure out like how old is it, okay? And how they date old things is usually using the half-life of elements like carbon-14. And the reason they use the half-life of carbon-14 is because it decays at a pretty stable rate. It decays at a easily detectable rate. So the gist of it is, if you've ever seen where they dug up something and they're trying to date it, they usually use processes like this because if it has a lot of carbon-14 in it, it means it's not very old. It hasn't had time for that carbon-14 to decay. If there's very little carbon-14 in it, it means that it's been there for a while, right? It's been decaying, and so there's very little of that trace element of carbon-14, okay? So the general form for exponential decay is going to look awfully close to the one for exponential growth with really just one change. So I'm going to use the same letters and everything. It's A equals A sub 0 times e to the negative kt power. Okay. So what do you note is different? Yeah, k is negative. And remember what negative exponents mean. Negative exponents give us fractions, right? So basically it's going to give us smaller and smaller fractions until they approach 0, or as they approach 0. So you're just going to be like whittling, chipping away at it. It's just going to be getting smaller, 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 smaller as we go to 0. Okay, so I'm going to give you kind of some stat formulas for some different countries, and we're going to use this in the next few questions. So population is something that most of the world takes really seriously. Okay, they want to track their population. They want to make sure they have enough resources for all the people that will be living in their country. So here are some general formulas for the population of some of the countries around the world. So that's India, Iraq, it looks like this, Japan, looks like this. And then finally we'll look at Russia. So really no particular reason to pick the countries I did. I just wanted kind of some varied locations. And for all of these, we're going to say that T is the number of years after 2006. So in other words, in 2006, we're going to call that ground 0 times 0. And then if it's 2007, we'll use time equals 1. If it's 2008, we'll use time equals 2, and so on and so forth.
Does Russia not have the E?
Oh, it does. Yeah, thank you. They all should have the same format, so that was a good question. So yeah, it definitely should have the E. So it's negative 0.001 T. So notice that all of these countries have different starting populations, and they all have different growth rates. In fact, one of them doesn't even have a growth rate, right? What's happening in Russia to the population? It's decreasing, right? So it's a decay, okay? So basically, their population is going down, which is pretty unusual, but does happen. So let's see if we can answer some questions. So which country, without a calculator, just by glancing at the formulas, which country has the highest population in 2006? Okay, and then I also want you to tell me which one has the lowest. And I don't want you, for this one, we'll get out our calculator in a bit, but I don't want you to use the calculator for this, because I actually don't think that you need to. Okay, because remember, 2006 is the start, right? So you actually know the starting populations of all of the countries, right? So which one has the highest starting population? India definitely has the highest starting population, right? Their starting population was 1,095.6 million. Just so you know, that's actually 1,095,600,000 is actually what that is. You don't really say 1,000 million, it's actually a billion. What about the lowest population? Iraq. Because they have how much? 26.8 million. Okay. Again, no calculator required for this next question either. So what if I ask you which country has the highest growth rate and which one has the lowest? Okay, so which number do you look at for the growth rate? You don't look at the a sub 0. Which number do you pay attention to when you're trying to figure out how fast they're growing? You pay attention to like the exponent after the e, right? So notice, by the way, if you change this to a percentage, this is 1.4%, right? This is 2.7%. This is actually 0.1%. So the highest one is actually what? It's Iraq, right? Iraq has the highest growth rate because they are increasing by 2.7%. So even though they have the smallest starting population, they're actually growing the fastest as far as percentage rate goes. What about lowest? We already kind of talked about this, honestly. Russia's definitely the lowest, right? Because they're actually the only country that's going down. So they're actually going down by 0.1%. Remember, when you change a decimal to a percentage, you move the decimal place twice. So it's not even 1%, it's actually negative 0.1%. All right, so what about this next question? What was Japan's population in 2006? And then what was it in 2008? So one of these doesn't require a calculator whatsoever. Which one won't require a calculator? 2006 is the beginning of what we're looking at, right? So we already know that value. We already know the starting amount, and I took the paper down, but you should still be able to look back at it. So what was the starting amount for Japan? Wasn't it like 127.5 million? Okay, but for 2008, we are going to need our calculator. How come? Because it's not the starting amount, right? It's 2 years later, okay? So we're going to use what value for t since it's 2 years later? We're going to use t equals 2, right? We're going to also use the formula for Japan, which was 127 e to the 0.001 t power. So we're just going to plug in what? Plug in t equals 2. Okay, so we're going to get that a equals 1,275, and then e to the 0.001 times 2 power. So your calculator can handle this, so you would just do 1,275 times e raised to the, sorry about that, let me get it out of the glare, 0.001 times 2. Okay, if you have an older calculator that doesn't open up an exponent box like mine just did here, then you need to put parentheses around the whole exponent, like the 2-part exponent. But you should get right around, and we'll just round this to the nearest 2 decimal places. So 1,277.55 million people. Okay. It probably shouldn't surprise us that the population didn't go up by that much, right? Why did it not go up by that much? If you look at Japan's rate, it's pretty tiny, right? It's actually 0.1%. So it's not going up by even 1% every year, right? So it's a pretty small increase. But notice that, like, it's not nothing, right? 0.05 million people is still a lot of people, okay? You're still actually talking about 50,000 people. So it's not a crazy big jump, but it is still a jump. All right, so what about this question? When will India's population be around 1,238 million if this growth trend continues? So the fact that I asked you when should kind of tell you what you're trying to find, right? What are you trying to find if I'm asking you for when? Yeah, you're trying to find t. Okay, but we're going to use the formula for India, which was, I think, 1,095.6, and then e to the 0.014 t power. So we've done problems like this before, but these numbers aren't as pleasant maybe as what we did before. Notice this is what we're actually trying to solve for, right? We want to get t by itself. And right now, t is kind of in an untouchable location. It's in the exponent. And so do you remember how we solve problems that look like this? The first thing we want to do is get rid of this number, right? We want to isolate the e part. The e part needs to be all alone, okay? So what that means, and by the way, I can go ahead and plug in 1238 where? Like, it's asking me when, right? So I can go ahead and plug it in here. And I probably honestly should have done that before. Because I know the final population, I'm just trying to figure out how long it takes to get there. So the first step, again, is to get rid of this number. So note, it's going to go away over here, right? And so I'm going to be left with, I'm going to move over here, 1,238 over 10,500, or sorry, 1,095.6 equals e to this power. That's what I've got so far. Okay, so the problem is that the t is where I can't touch it right now. Okay, so what did we do to kind of undo e before? What do I need to do to both sides? Yes, I need to take the log of both sides. Which log should I definitely use because it's e? Yeah, I should definitely use ln, right? So take the ln of both sides. So I'm going to rewrite that so I've got some room. I've got 1238 over 1095.6. Don't even try to mess with that. Just leave it as it is. The calculator can handle a fraction that looks like that, so don't try to simplify it because then you're going to be rounding in the middle of a problem. And you really only want to round once at the end. So I'm going to take the ln of both sides. So why is that helpful to me? What do the ln and the e do to each other? They cancel each other out, right? And it also allows this guy to move out of the exponent spot. So we end up getting 0.014t, and then equals natural log of this weird fraction. But we're actually one step from being finished. Why do I say that? What's the last thing if I really want to know what t is? What number needs to move? This decimal, right? So when I want it to move, I just divide by it. So I end up getting that t equals this weird ln fraction divided by 0.014. Okay, so I'm going to let my calculator handle that for sure, right? That's not something I can do in my head. So ln of 1238 divided by 1095.6. And then close your ln because you're finished with the ln part. And then we want to divide by 0.014. So again, we'll round this to 2 decimal places. Pay attention on MyLab. It'll usually kind of tell you what you get. But we end up getting 8.73. But remember, this is actually years after 2006. So in what year is this going to happen then, if we start counting in 06? So it's actually going to be 8 years into it, right? So it's going to be in 2014. But it's actually going to be later in the year in 2014. Why do I say that? Because it's like 8.73, right? So it's actually like almost 3/4 of the year through, right? So that would be almost 9 months. 9 months into 2014. Okay. So how you're going to know that you need to use logarithms is anytime what you're trying to solve for is in the exponent spot, you've got to use logarithms to solve. So when will Russia's population be 140 million? If the trend continues? So I wanted to do one with Russia just because it has a negative exponent, but to be honest, it's not really that much different from what we've already been doing. But again, because I asked you for when, what am I asking you for again? T. We want to know what time is. So we're going to use the formula for Russia, which was A equals 142.9, and then E to the negative 0.001 t power. So the first thing is we use the 140 million and we put it in here. Okay, we know the final population we're trying to track is going to be 140. And it's okay that it's smaller than what we started with because it actually should be for Russia, because what's happening in Russia? Decreasing population. Okay, so we're going to do it the same way that we did before. We're going to get the E part by itself, and then we're going to use what to get rid of the E? ln, and then we'll proceed from there. So first we got to get rid of the 142.9, and we do that by dividing. So then this goes away, and we get 140 over 140.2 equals e to the ugly decimal power. And then just like we said before, we're going to take the ln of both sides. So that's going to get rid of this and move this where? To the front. So we'll end up getting natural log of the fraction on the left. And then we'll get the decimal times t on the right. And then one more time, we're almost there, right? So we'll divide by the decimal. And then we'll just let the calculator do the rest, right? So we should end up getting that t equals the natural log of 140 over 142.9 divided by this negative quantity. So what you end up with is about 20.5 years. So again, we don't just leave it there. We need to add that to what? What year did we start counting in this problem? 2006, right? So it's actually going to be in 2026. Okay. And actually, if you want to be more specific, it's actually halfway through the year. Because of the 0.5. But it's not enough to, tick us over to the next year. So essentially, that's really all that we're doing today. We're going to be looking at different equations, but we're really just kind of focusing in on the problems where the variable is in the exponent spot, and we're going to use logarithms to get it out of the exponent spot. That's really pretty much it. So we looked at some growth problems. Let's look at some decay problems. I don't want y'all to look at these and think that you don't know how to do these. They're really just the same. You just have to remember that we have a negative exponent, and we did that in Russia's population anyway, just a minute ago, right? All right, so let's say that a substance, Krypton 85, has a decay rate of 6.3% per year. And the question is, what is its half-life? And so in case you don't know, let's go ahead and define what half-life is. Half-life is literally the number of years it takes for half the substance to decay. So again, this is how we date old artifacts. If we know how quickly the element decays in the item we're talking about, then we can estimate how old the item is based on how much is still left. All right, so notice I don't have a formula really given to me, so I'm just going to start off with the general formula for decay, which looks like this. A equals A sub 0, and then e to the negative kt power. So let's go ahead and plug in the things that I know. To be honest, I don't really know A sub 0, so I'm going to leave that alone. Like, I didn't tell you that it has such and such quantity of Krypton 85 at the beginning, right? I didn't tell you that, okay? But I did tell you the what. What part did I let you know about? I let you know about the rate, right? So if the rate is, and by the way, it's a decay, which means it's what kind of rate again? It's going to be negative, right? So it's going to be negative 0.063 t. Note, I moved the decimal place twice, so that's why it's 0.063. And then it's negative because we're talking about decay. So notice that we can't really have more than one variable, so we're going to have to think about this for a minute. So if we start off with whatever we start off with, it doesn't really matter what we start off with. What are we supposed to end up with if we're talking about half-life? Half of what we started with, right? So whatever the starting amount is, we're going to end up with half of what we started with. Okay. So I know this is weird, but notice when I try to get rid of the A sub 0, it's actually kind of nice, right? Because what happens? You divide both sides by A sub 0, and what happens on both sides, actually? That goes away, right? So you end up with just 1/2 equals e to the negative 0.063 power t, or 0.063 t power, I mean. So now what? If we want to know what t is, what do? Same as before. Take the what? Natural log of both sides, right? Whatever you do to one side, we have to remember we have to do the same thing to the other. And the purpose in that, of course, is that this is gone, right? And this is going to move where again? To the front, right? So we get the natural log of 1/2 equals negative 0.063 t. And so we're one step from being done. We just need to divide by what? That decimal, right? Now, we should not get a negative answer. How come? What are we solving for again? We're solving for t, right? T can't be a negative number of years, right? We can't go back. It's not Back to the Future, right? We can't time travel. This one, usually you will be told how to round it. So let's just say I asked you to round this to the nearest year. So we would use our calculator, and we're going to do ln of 1/2. And then divided by the negative 0.063. Okay, and notice it's really pretty close to 11 years. So what that means is that every 11 years, this Krypton 85 is halving what it has, right? What's it eventually going to get really close to if it keeps halving over and over and over? It's going to get close to 0, right? If you keep halving something and you keep splitting it in two, then it's just going to get smaller and smaller. Okay, so I want to do another one kind of like that, but we're just going to switch up elements. Don't think you really have to know anything about chemistry to be able to do these problems. You don't, okay? So if uranium-238 has a half-life of 4,560 years, and let's say I asked you to find the decay rate. So I'm not asking you to find T this time, right? What am I asking you to find this time? I'm asking you to find the K, right? Like the decay constant in this case. Okay, but I'm still going to use the general formula. I'm still going to use A equals A sub 0 e to the negative kt power. By the way, before we continue, if it takes 4,560 years just to half it, that's a really slow decay rate, right? Like that takes a really long time to happen, so we should expect an answer that's going to be pretty small. So we're going to do a similar thing to what we did in example 6. If A sub 0 is our starting amount, then what would the half-life be? Half of A sub 0, okay? And then it would be e to the negative k times 4,560 years power. So if you're paying attention, this is actually very, very close to the one that we just did, because we're still going to have to get the e part by itself, and we're still going to have to take the what of both sides when all said and done. We're still going to have to take the ln of both sides, right? So those things are gone, and I get 1/2 equals e to the negative 4,560 k power. And then I'll ln both sides. Make sure you know that like ln is an operation. You're not multiplying both sides by ln. It's got to be ln of something. So you're taking the natural log of both sides. Okay? So kind of a small discrepancy, but I want you to know that that's the case. So you end up with ln of 1/2 on the left and negative 4,560k on the right. So what would you do to find your answer in the end? Divide by what? By the negative 4,560? So I want to talk about what you get here on the calculator and what it means for you, okay, so that you aren't thrown off by the fact that this answer is a little weird in the calculator. So let's go ahead and punch it in. Either do it on your own or look up here. So notice when I divide, I get a really weird answer, and if you're in the back, I don't know if you can see, but so notice that you get a big decimal and then e to the negative 4th power, okay? So just to be clear, I'm going to slide this over. This is how your calculator handles numbers that are kind of unpleasant. So if you see 1.52 e negative 4 on your calculator, it's trying to tell you its scientific notation. So it actually means, and you do need to know this, 1.52 times 10 to the negative 4th. Okay, E stands for exponent on your calculator, so it's telling you that this number is super, super tiny. Okay, and by the way, what scientific notation means, if you've forgotten, because it might have been a minute since you looked at it, but it means move the decimal 4 places to the left. That's what it means. So I'm going to just kind of box this in because it's just something that you need to know. If it's a positive number after the E, it just means move the decimal place the other direction. So in other words, K is actually going to be this decimal where you moved it over 4 times. So it's actually going to be 0.000152. Or if you wanted to enter that as a percentage, you would move the decimal place back 2 for the percentage, so it would be 0.0152%. So just like we thought, it's a very, very tiny K, right? It's not changing that quickly. And so actually that would be something valid that we could use to date artifacts because it's not changing all that much. Okay, so let's do one more. If you get a question on your homework about specifically carbon-14 dating, you can use the information from this problem in order to do that one that you get on your homework. So let's say that prehistoric cave paintings were found with 15% of their original carbon-14. For carbon-14, K is about 0.000121. So that's what I mean on your homework. If you get one with carbon-14, you can use that K. It's actually the case for any problem involving carbon-14. And so let's say I wanted you to find the age of the paintings. So if you ever wondered like how they're dating these old things they find, this is how they're doing it. It is an estimate though, okay? And particularly for elements that are radioactive, it can be a little bit unstable as far as how much they decay, okay? And carbon-14 is actually a radioactive element if you care about that quality. But we're going to use the decay formula. So I guess my point is that's why in real life they're wrong sometimes, because it's not always the most legit format of dating something, but it's better than the alternative, which is just to make a guess about how old it is. Okay. All right, so let's kind of take the same strategy that we did before, right? We don't really know what the starting amount was, but we know that it ended with what percentage of what it started with? 15%, right? So we did note, remember when we did half-life, we did a half times what we started with? So if we want 15% of what we started with, we're just going to use the decimal and say literally 15% of a sub 0. And then it's going to be e to the negative 0.000121 t power. And then notice once we get it set up, it's really close to the previous two ones that we did, right? We're going to divide by a sub 0. So a sub 0's go away, and we're going to get 0.15 on the left, and then e to that really, really tiny decimal on the right. And then one more time, we're going to take the what of both sides? The natural log, okay, which is going to cancel these and move this guy to the front. So on the right, I'm going to get negative 0.000121 t. On the left, I'm going to get natural log of whatever I started with. So To finish it out, I just divide by the decimal, just like I have been before, which is going to get rid of those, and then I'll be able to tell approximately how old it is, okay? If it's a prehistoric cave painting, are we expecting it to be old or not that old? It's going to be old, okay? So don't be surprised when you get an answer that's really, really a lot of years here. Divided by negative 0.000. Make sure when you have a decimal like this, you put the right number of zeros. 121. So notice it's right around 15,679 years old. Okay, so the reason they found it to be so old, by the way, is because a lot of the carbon-14 was already gone from it, right? It was only 15% remaining, so that's how they knew that it was super, super old. All right, so the gist of really all of these problems are when you have an exponent and the variable you want to know is in the exponent, what do you do to both sides to kind of handle that? You take the log of both sides, right? In this section, we happen to be using all E problems. So which log are we using every time? ln. But in other sections, remember, if it's not E, you have a choice to use log log, the common log, or ln, the natural log. Okay.